let's see if this works. Okay, good. All right, so so these are our basketball players, 5 of them. 76 inches, 78, 79, 81, 86. Okay, inches tall. So we could make, if we chose samples of size 2, we could make 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. There's 10 actual distinct samples of size 2. Okay, so I'm going to take each of those samples of size 2. So this is telling you which 2 players, and then their 2 heights, and then the mean of a sample mean for each of those samples of size 2. So what we see here is when we look at all of those samples of size 2, that x bar, that sample mean itself is a variable, right? Because that changes from sample to sample. You have a different sample mean for each sample. So we could look at the distribution of the sample means. We can make a distribution. So far we've just been looking at distributions of, say, the variable, just the values of the variable. But now we can take, say, all the samples of size 2, get those means, and then make a distribution of that variable. Okay, so that's what this chapter is about. Okay, so here's this. So for a variable x and equally sized samples, the mean of a sample is itself a variable. Its value varies from sample to sample. So we can investigate the distribution of sample means. And that distribution is called the sampling distribution of the sample mean. So sampling distribution of the sampling mean. So whenever you take a particular statistic of samples, you can look at those values in its own distribution. And so we're just going to look at sample means, right? Sample means. So a sampling distribution is looking at a particular statistic about the samples and looking at the distribution of that. Okay, so this has to make a lot of sense. This concept has to be in place as we're talking about stuff in this chapter. So I want to make sure that this idea makes sense. Do you get what we're doing? Anybody have a question? Okay, so let me go back to the last slide. So this slide, so we took samples of size 2. Does that make sense? And then we took the mean of each sample. So that mean of each sample is a variable, you see? So we could take the distribution of these numbers. So make a like before we were just doing the distribution of the values of the variable. But now we're doing a distribution of.
So do you find the average of those ones?
Yeah, so we could find the mean of those and the standard deviation of those. Exactly. Okay. Yeah, so as its own distribution, we find things like the mean and the standard deviation of those. Yeah, exactly. Okay, so here is the population distribution as a dot plot. Okay, there's our 5 heights, 76, 78, 79, 81, and 86. Okay, our population mean 80. So now if I plot the means of the samples, remember those 10 of those. So here's the dot plot for the sampling distribution. Here are the means of all samples of size 2 that we took from the original population. And what do you suppose the mean of the sampling distribution is? So if we take all samples of size 2 and find their means, and then take the mean of all that, what do you suppose it is? Is it lower or higher than 80? Or is it 80? It should make sense that it's 80, right? It should make sense that it's 80, okay? And so so this is the mean of all the x bars, right? The mean of all the x bars. So the fact that you evenly took you took every pair of 2 That's going to make it, and then when you take the mean of that, you're going to get 80. Right? You're going to get the same mean that you had for the original 5. Okay. Does it make sense? If I start to lose you, speak up and ask. Okay. So this is x, is the variable x, and this is the variable x bar for samples of size 2 as a distribution. Okay, so this is what we talked about. For samples of size n, the mean of the variable x bar equals the mean of the variable under consideration. And that's what we just saw. If you have the population mean, then your mean of your sampling distribution is going to equal the population mean. Piece of cake, right? Easy. But what about the standard deviation of a sampling distribution? What will happen to the standard deviation of this new distribution of sample means if your sample size increased? So if you took a bigger sample size and then found that, what would happen to the standard deviation? Would it increase or decrease? So here's our n equals 1, or the population first, and then here's n equals 2. So this is samples of size 2, that's the one we looked at. So what do you see happening to that data? Is it getting more spread out or less spread out? Less, right? So what will happen if we take n equals 3? Yeah, so every time you take larger samples, you're more likely to get a sample mean closer to the population mean, right? You're not going to have these outliers, right? So this is the mean of the 2 highest, right? But now if you take the 3 highest, it's going to be low. That mean will be closer to the actual mean population. So here's for n equals 3. This is what you get for the dot plot when n equals 3. So taking groups of 3, your sample means will be tighter, closer in to the actual mean. That makes sense. Here's n equals 4. And then n equals 5 is just going to be that there's only one sample of size 5. Its mean is 80, so there's just the one. So this is a really important principle. As you take larger and larger sample size, the resulting distribution of sample means is going to be more tight around the mean. So the standard deviation is going down with a larger sample size. Okay, and here's how you actually calculate it. You take the standard deviation of the population and you divide by the square root of your sample size. Which makes sense what we just said. For a larger n, what would happen to that ratio? If you make the denominator bigger, the ratio goes down, right? And so then we're talking about less spread of the data. So you really have to have a kind of firm grasp of what we're talking about. You've got the population distribution, and then we're taking samples and getting all their means, and then looking at the distribution of those means. That distribution of means will become tighter and tighter as you choose larger and larger samples, as we saw in the last slide. Okay, let's try some examples here. So the mean living space for single-family detached homes is 1742 square feet with a standard deviation of 568 square feet. So now we're going to take samples of 25 single-family detached homes. We're going to determine the mean and standard deviation of the variable x bar. So this is a sampling distribution. So this is, what is our variable? So let's say, so what is our variable x, first of all? 1,700. No, like what is the meaning of the variable x? So what are we looking at? What is x? What's that? The living space. In? Square feet. So it's the amount of living space in square feet. That's a good, very good habit to get into when you come to a context. Make sure you know what your variable is. Amount of living space in square feet. Okay? So then the 1742, what symbol do we have for that? It says that the mean of living space is 1742. So is that mu or x bar? Is that this thing or is it this thing? The 1742. Okay, it's the first one, right? This is like the population mean. This is the population mean. So our mu is 1742. And then standard deviation, that's a population standard deviation of 568. So now we want to take samples of 25 homes. And so that's our n. N is the sample size. And we want to find, so now we're going to take, imagine taking samples of size 25 and making a distribution out of that, out of the means of those samples. So what will the mean of those samples of size 25? And that would be this, right? So mu is the population mean. X bar is a particular sample mean. So x bar is the variable for a. So you pick a particular sample. There's an x bar. There's a mean of that sample, and then there's different means for different samples. So it's that variable x bar is the sample mean, and so then this is the mean of the distribution of means, right? This is the mean of the distribution of means of samples of size 25. And what is it? It's going to be the same as our population. Square feet. Okay? And then what about standard deviation of the sampling distribution? Standard deviation of the sampling distribution. Will it be 568? No, because when we take samples of size 25, that's a pretty big sample. So you're likely to get mostly values near, a lot of values near the mean when you take those samples of size 25. So the means of those are going to be tight around 25. So a lot tighter around 25 than the actual population. So we're going to do 568 and then divided by square root of 25, square root of the sample size. That was what I just showed you on the previous page. And so we're basically doing 568 over 5. Somebody tell me what that is. Nice and loud? Thank you. And that's also square feet. So we got lots of symbols and lots of means flying around here. You got to know what the meaning of everything is. What's the meaning of mu? What's the meaning of x bar? What's the meaning of mu of x bar? Do you understand that? It's really crucial. Okay, so now we have a distribution, just like what we've had before. We have a mean and standard deviation of sample means. So we can do answer all the same questions we've asked before. So for samples of size 25, what's the probability that you pick a sample of size 25 and its mean is less than 2,000 square feet? So what's the probability that a sample of size 25 has a mean less than 2,000? Can you do it? What would you do? So I just made up this question. It's part C. You don't have to pay me at all. Okay, it's free. So what's the probability? A sample has a mean less than 2,000 square feet. Sample of 25. What would you do? How are we going to do that? I know Danielle knows. So just because test 1 is over doesn't mean we forget everything. Find the z-score, right? So we go at a distribution, and we want a z-score for 2,000. Felipe, how would you do that?
Minus 1742 over 114.6.
That's it. Right? It would be your particular value of the variable, in this case, 2,000 minus the distribution mean over the distribution standard deviation. And what's our z-score for that? 1 point something? 2.27? And then you get your chart out? And we get a percent. As soon as you get it, shout it out. Was it?
98.84.
Did you find the right number? Someone else agree with that? I got a nod over there. Which, does that make sense with our ranges? Yeah, because 2, right? 2, between plus or minus 2 is 95% of the data. So if we're above 2 and we're going all the way less than, we know it's going to be something really big. Okay, why don't you try the baby weight one, just for sample size 200, okay? This is piece cake, right? So this is easy so far. So for 7.47, try A and B. A and B on the next one. Anybody have a question on this example? So try A and B. Do a watch. Okay. Okay, how'd we do? So let's see here. Jessica, did you get started on this? No? So what about, did you get the variable? What's the variable in the population? The variable is birth weight. That's right. In grams. What's the population? What are we looking at? Birth weight in grams. No, the population would be like what the weight of what? The weight of what? Right? Babies. Population is like all babies. And we're looking specifically at their birth weight. Okay? And what do we get do we have a population mean? A population standard deviation? Mean birth weight 3369. Standard deviation 581. Okay, so now that's A and B. So we want a sample of size 200. What's going to be the mean and standard deviation of sample means? If the size of the sample is 200, what's the mean and standard deviation of sample means? Selena, did you get it? How about the mean? What's the mean of these sample means going to be? Right, so the mean of sample means is 3369. And then standard deviation of sample means? Jason, did you get it?
Yeah, 581
581 over radical 200. 41.1. Okay, so imagine this. You're taking samples of size 200. If you take samples of size 200 babies, where do you expect that mean to be very close to? Right? If you get that's a huge sample, right? 200 is a really big sample of baby weights. So you're going to expect that that your samples have a mean really close to the population mean. You're taking such large samples. So if you looked at all the means of those samples of size 200, you expect them to be very close to 3369, which means our standard deviation is high or low? Low. It means that all those sample means for a large sample, all those sample means are going to be really close. You're going to expect them to all be really close to 3369. And that's what we're seeing, that 68% of samples will have a mean within 41 grams of the actual population mean. Right? This is very low relative to 3369. That's a low standard deviation. Why? Because our sample size is so big. We expect the means of those samples to be real in close, tight to that 3369 number. That's what we're finding. Okay, any questions? So make sure it's not that you can just do these calculations. The calculations are kind of the easy part. Can you interpret what's going on, and can you predict what's going to happen, like the questions that I'm asking outside of these just numerical calculations? Make sure you're tracking with me. Okay, sampling error is the result from using a sample to estimate population characteristic. In other words, how far a sample mean is from the population mean. So we say we take one sample and we get a mean from that sample. The error then is the distance that is away from the actual population mean. That's how much error there is. Should make sense, right? So in that previous example, what was the mean baby weight again?
3,369.
Thank you. Okay. And so if we take a sample and its mean is 3,000, then the sampling error was negative 369. So I think maybe it would make more sense to say the absolute value. Distance away. So 369. Grams. So we're 369 grams away in our sample mean from the population. In terms of trying to predict the actual population mean, that had an error of 369 grams. That particular sample had an error of 369 grams. Make sense? So now, again, like we're talking about inferential statistics. You got a sample, you want to try to predict the population mean. Well, if you just have one sample, then or even multiple samples, there's going to be error. There's going to be error. And so in this case, if your one sample is 3,000, that's the best thing you know. If you just have that one sample, that's all you know for what the mean could be. That's your best guess, and your error in that case would be 369 grams. Okay, so here's IQs measured on the Standard Revision of, this is the IQ scale. IQs are normally distributed with a mean of 100 and a standard deviation of 16. So those are our population. That's our population statistics for IQ. Mean of 100, standard deviation of 16. So now we look at sample sizes of sample size 4. Okay, so now n equals 4, and we're going to look at the sampling distribution of the means of those samples. And so here's a simulation they ran with a computer. So here is our, this is what? Means of samples of size 4. That's what these are, means of samples of size 4. So does this have a greater standard deviation or a lesser standard deviation than 16? Use samples of size 4. Is the standard deviation of this larger or smaller than 16? You should be able to answer that.
Less.
2 people are saying less. Agree with that? Yeah, because when you start taking samples, now your tendency is going to be to get a mean that's close to the mean. Closer to the mean than just the mean of all individual values. Okay? When you take samples, you're grabbing 4 at random. Well, your tendency is going to be to get means closer to the actual population mean. And then the bigger the sample, the more that tendency is for that mean to be close to the population mean. All right? So so how much less is it? So samples of size 4, what is our sigma x bar is going to be 16 over or 8, right? So it's half as big. Samples of size 4 make the distribution of means have a standard deviation half as much. So twice as tight in. Okay, so this is showing the idea that if you start with a normal distribution, then the distribution of means of samples is also going to be normal. This is just evidence of that. Use a simulation to make plausible the fact that x bar is normally distributed. Well, we're looking right at it. So this is a simulation of samples of size 4, and it's looking a whole lot like it's a normal distribution. And that, in fact, is true. That if you start with a normal distribution, then a sampling distribution of means will also be normal. Okay, so here this says that. Suppose that a variable x is normally distributed with a mean mu and a standard deviation sigma. then for samples of size n, the variable x bar is also normally distributed. That's the key. That if you start with a population is normally distributed, then the variable x bar is also normally distributed. And this we know has a mean of mu and standard deviation of, we'd already talked about that. But this is the big point of this slide. If your population is normally distributed, your sampling distribution of means is normally distributed. So what about the standard deviation of sampling distribution? What happens to, yeah, we already talked about that. We know that it goes down, right? When you take larger and larger sample size, your standard deviation gets smaller. And so let's see that here. Here's a picture. So here is the population distribution. Samples of size 4. So what would you expect that the distribution to look like if you were to sketch it? Same scale, right? So 52 to 48. Showing 52 to 48 on scale. Also showing 52 to 48. 52 to 48, 52 to 48. So if we were to just make a rough sketch of this distribution, how would you sketch it? Kelly? Closer together? That's right. So that whole this whole thing would be scrunched together if you take samples of size 4. And we saw it. We calculated it last time. That the mean is still, the mean of the sampling distribution is 100. Standard deviation is 8, right? 16 over square root of 4. Now what about samples of size 16? How would you sketch this one? Draw it with your finger. Everyone draw it with your finger. Everyone. Tall and skinny, right? That's the point. You're taking very large, these are getting to be larger samples now. You'd expect IQs, the sample, the means of those samples of 16 to be close to 100. And what do we get? Well, now we get the standard deviation of 4. The 16 divided by square root of 16, which is 4. Okay, what about non-normally distributed populations? What about non-normally distributed populations? Sorry, I'm gonna watch. Okay. All right, so here, is this left skewed or right skewed? Right skewed. The median is around 2 or 3. The mean will get pulled to a greater value. That's right skew, right? Right skew. And so what about the shape of the sampling distribution of the sample mean? Will it be skewed or will it be normal? You think it'll be skewed? So if we take, so what we're guessing maybe is if we take samples and we look at the distribution of the means of the samples, it will also be skewed right. Is that what we're saying? Okay, let's take a look at it. So here's 3 different distributions. This is normal distribution. This is J-shaped, but it's pretty much similar to a. This is very similar to a right skewed distribution. And then here's a uniform distribution. So if you take samples of size 2, here's what the distributions look like of the sample means. So the first one we know, right? So if we talked about earlier, if we have normal distribution, the sampling distribution of means will be normal, okay? And will have a smaller standard deviation. We've talked about that. So what? It's still normal, but it's tighter in. So we see that this right skewed distribution here continues to have a right skewed distribution. And then this normal distribution, well, a uniform distribution, meaning the variable gets the same frequency across for all values. It starts to look like this, right? It starts looking like your means are going to be closer to the middle. All right, here's getting towards larger samples, size 10. Here's what happens. We know our normally distributed population will just still be normally distributed with a smaller standard deviation. What's happening to our right skewed distribution. So this is the one we want to focus on, the middle column here. What's happening when we have larger samples? It's becoming normal. You see this? When you start taking larger samples, your distribution of the means begins to turn to a normal distribution for larger and larger samples. And so here's n equals 30. All of them, see, all of them for large samples, no matter what shape of a distribution we started with for our population, for larger samples, you get a normal distribution. And 30 is kind of the magic number. Around 30 is where the distribution of means is normal or very close. So 30 is somewhat of a baseline sample size that's big enough for the distribution to become normal. Okay, so this is what the central limit theorem. Central limit theorem says that the variable x bar is approximately normally distributed regardless of the distribution of the variable to start with. Okay? But this is for a relatively large sample size, right? For a relatively large sample size, and we said that the number is roughly 30, okay? That 30 is roughly large enough. No matter what starting distribution, the shape of your distribution is to start with, when you get up to samples of size 30 or larger, your distribution of sample means is going to be normal. That's what the central limit theorem is. Yeah?
So every sample mean if the beginning one is skewed, then it will be skewed unless it starts getting bigger, then it's going to start becoming normal.
Yeah, so if you have skewed distribution and you have small samples like around 5, yeah, you're gonna have your distribution will be skewed like the population was. But like we saw, when you get up to like 10, it's gonna start becoming normal. And when you get to 30, it's gonna be normal. But the central limit theorem says that a distribution of means will be normal for large enough samples like 30 and bigger. Okay, so here's going back to that one that we said was right skewed. So this is 1,000 samples of 30, of size 30. So they took 1,000 samples of size 30 and asked, in terms of number of people in the house, and then look at the data. The data is clearly normally distributed. So this is just showing that if you have your samples large enough, in this case the sample size is 30, you get a normal distribution, even if your original distribution is not normal. So this is just a summary of what we've talked about. So let's just try one example and we'll be done. So this is times in the 10K run. So our variable is finish time in the 10K in minutes. And they gave us a mean finish time of 61, standard deviation 9. We want samples of size 4. So can you put together the distribution for samples of size 4? So first of all, samples of size 4. Is it big enough to get us a distribution that's normally distributed? So is our resulting distribution of means of samples of size 4 going to be normally distributed? Lots of nods. What's that?
If the top one is.
Right. So no. So you don't need a large sample size if what? If your original distribution is normal, and that's what we have. See, so the finish times are normally distributed in the first place. Then you don't need the large sample size. Any sample size now will result in a normal distribution of sample means. Okay, it's when you don't have a normal distribution that you need the big samples. But if you have you're starting with a normally distributed variable, then any sample size will result in means that are normally distributed. Okay, so what's going to be our sample? So our distribution will be the mean of means. 61 will be the standard deviation of means. Remember what we do? 9 over square root of 4. Is that 4.5? Minutes. Okay, we know it's a constructed graph. We want the percentage of samples of 4 finishers that have a mean finishing times within 5 minutes of the population mean. Can you do it? So we can sketch we sketch X bar, right? So here's 61, and what was the trick to making it right? Oh, that's bad. We do better than that. Remember I gave you that trick? So it's like, it's kind of flat, and then it's flat up here, and then where it's curved the most was how many standard deviations? 2. So 9, so 70. We're going to go up 2 and down 2. So 52. Okay, and so they want to know what percentage of all samples of 4 finishers have a mean within 5 minutes of the population mean. So what am I looking for? Within 5 minutes of 61 would be up to 66, right? And 5 minutes. 76? 56? Is it going to be 68%? Is it going to be 68% in between 56 minutes and 66 minutes? Yes or no? More or less?
Less.
Why more? Yeah, 1 standard deviation would be 4.5 above and below, but they're saying 5 above and below instead of 4.5. So it's going to be slightly bigger than 68, right? We expect something around, let's guess. What would you guess?
70.
Sounds good. Okay, let's do it. So let's figure it out. Let's see how our guess is. So he's guessed about 71% of sample means will be between 56 and 66. So quick, do it. So Kesman, tell me what you're doing.
I subtracted, after subtracted 61 from 6 divided by 5.
So you're finding a z-score? And you said 66 minus 61 over
6 minus 61. Whoa. Let's do the same thing. Which step is 66? So divide by 4.5.
4.5. And then we're going to find another one that's
56 minus 61.
right. Over. Anybody got those? This is 1.11. And so is this negative 1.11? And from the chart, area to the left, point. Nice and loud. 8665. Area to the left of negative 1.11. 1335. How do we find the area between? Subtract. And you get 0.71. 33? Okay, pretty good guess. 71%, or in this case, it's 73%. Now, here's the key. Can you interpret that correctly? What is that? 73.3% is what? Anyone want to give it a shot? Here you go.
The percentage of all samples of ore that finish within those 2 times, or with the mean with those 2 times.
Good. All right, so it's this probability that a sample of size 4 will have a mean between 56 and 66. Probability that a sample of size 4 will fit between those two. So make sure when you're doing your homework, you're practicing interpretation. It's going to be on the test and the quizzes. Not just calculating the numbers, but interpreting the numbers. Okay? Sundays, my stat lab homework will be up this morning. Okay? So you can start working on it.